How many students have solved this problem, Amma? How many students had solved this problem that has a case 1 as well as case 2? So it is very important problem, Amma. We need to solve it. The values will be varying for different problems. The procedure will be same. The procedure will be same. The values will be varying for the different problems. Therefore, it is the important procedure for the second unit. That is, sorry, second chapter. Volumetric strain. So next, we need to derive a relationship between the Young's modulus and bulk modulus. Young's modulus and bulk modulus. We need to derive a relationship between the Young's modulus and the bulk modulus. So what is bulk modulus? We have know the Young's modulus. The Young's modulus is nothing but it is a ratio. It is a ratio of stress by strain. It is a ratio of stress by strain. It is a ratio of stress by strain. So next, what is a bulk modulus? So bulk modulus is also a ratio. Bulk modulus is also ratio of stress by volumetric strain. Volumetric strain. So here we need to consider the direct stress, which is also called as a perpendicular stress, which is also called as a perpendicular stress, which is also called as a perpendicular stress.
Sir, clearly let's blur కనిపిస్తుంది.
ఓకేనమ్మా? So here bulk modulus is an elastic constant. Bulk modulus is an elastic constant.
సార్ క్లియర్ గా కనిపించట్లేదు సార్. స్క్రీన్ షేర్ క్లియర్ గా కనిపించట్లేదు సార్, క్వశ్చన్లు కనిపించట్లేదు.
ఇప్పుడు క్లియర్ కనబడుతున్నాయమ్మా?
సార్ వస్తుంది సార్.
So bulk modulus is nothing but stress by volumetric strain. So previously we have discussed that bulk modulus is applied in three-dimensional view. It is an elastic constant applied in three-dimensional view. Three-dimensional view. Therefore, three different stresses, sigma x, sigma y, and sigma z. Sigma x, sigma y, and sigma z are applied on the component, which is all are equal, which
Sir, screen can be clear, sir.
on all the faces, which are equal on the faces, and we are considering a cube which having the same sides, that is L. Length is L, width is L, and thickness also will be L. We are considering a cube for deriving the relation between Young's modulus and bulk modulus. How to achieve a common stress on all the faces? How to achieve a common stress on all the faces? We can achieve by getting the common area that is on the faces, as well as the load applied on that area are equal. Mutually perpendicular loads applied on the faces are equal, then we will get the common stress. Or we can dip this type of body. We can dip this type of body in a hydrostatic, that means in a liquid. Therefore, equal pressure will be applied on all these six faces. Equal pressure is applied on all the six faces. Therefore, the stresses involved inside the body will be equal in all the directions. Therefore, here very, very important is the common stress. The common stress is applied along the x-axis, along the y-axis, and along the z-axis. That common stress is considered in bulk modulus. Divided by volumetric strain gives the bulk modulus equation. It is the ratio of direct stress by volumetric strain. Now I need to derive this relation. Very, very important relation. what is the relationship between Young's modulus and bulk modulus? What is the relationship between Young's modulus and bulk modulus? To derive this, I am considering a cube. I am considering cube whose length is L. That means in x direction, that is length is L and width is L and thickness also L. Thickness is also L. So three-dimensionally we have same lengths. Therefore, the volume of a cube can be written as L cube. So initially we have derived it as L into B into T. Volume of a rectangular bar. Here instead of B we have a L, instead of T also we have a L. So we will getting a L cube. That is the volume of a cube. Next, due to the external load applied on this cube, we are observing that delta L is the length change, in x-axis. I am considering as x-axis. And sigma is the stress applied along the x, along the y, and along the z axis. And mu is the Poisson ratio, and E is the Young's modulus of that material. Now I need to consider only one phase. And I need to consider only one load. Either in x-axis, either in y-axis, or either in z-axis to derive this relation. So here he is considering the strain along the AB direction. So AB, this is the A and B, and the load is applied in this direction. I am considering only this load. So due to this external load, we will get a strain, a longitudinal strain along the AB direction. And due to the y directional force, we are getting a lateral strain in AB. We are considering only AB, but the load are considered in three-dimensionally. And next, the strain in AB, when the load is considered on the opposite side, that is Z direction. This is the lateral strain. So we can combine the relation, that is the total strain along the AB. That is the strain along the AB. That is nothing but delta L by L can be written as in terms of, we have proved this in the previous class. Next, the original volume of a cube is V into L cube. The change of length is delta L, and the change of volume is delta V. So if you differentiate the second equation, we will get a relation that is delta V is equal to 3 times of L square into dl. Now I need volumetric strain. I need volumetric strain, that is nothing but change of volume by original volume. Therefore, divided by original volume, we are getting 3 into delta L by L, where delta L by L is derived as, can be derived as sigma by E into 1 minus 2 mu. Therefore, I can substitute in bulk modulus equation. That is stress by volumetric strain. Therefore, here stress and stress will be cancelled. We will get a relation. Capital E is equal to 3K 1 minus 2 mu. 1 minus 2 mu. This is the derivation for the relationship between Young's modulus and bulk modulus. Sir, ఈ డెరివేషన్ నాకు కొంచెం బిజీగా ఉంది, కష్టంగా ఉంది అనుకుంటే ఈజీ డెరివేషన్ ఒకటి ఉందమ్మా. We have derived that volumetric strain is sigma x, sigma y and sigma z by capital E. 1 minus 2 mu. Already volumetric strain గురించి ఈ డెరివేషన్ మనం డెరైవ్ చేసాము. In this problem, sigma x is also equal to sigma y, which is also equal to sigma z. Therefore, I can write it as 3 sigma by E into 1 minus 2 mu. It is volumetric strain. So I need to cross multiply it. Therefore, E is equal to 3 into sigma by volumetric strain into 1 minus 2 mu. I can write it as this term as K. Therefore, we are getting a relationship between Young's modulus and bulk modulus. So if you see here, it is a 3-dimensional. So we are getting a 3 in front of K. How to remember this equation? So it is a 3-dimensional. We need to have 3, 2 and 1 numerical values in my equations. 3, 2, 1 need to be there in my equation. Therefore, 3 in front of K and 1 minus 2 mu is the relation we need to by heart here. Next, second relation is I need to prove a relationship between Young's modulus with shear modulus. We need to derive it. So how to get a shear modulus? So if you observe this, a component, a shear force is applied on it. A shear force is applied on it. Due to this shear force on the area, tangential area, we will get a shear stress. It is represented by tau. It is represented by tau. So making this an equilibrium condition, we are applying only on the top face. We are applying only on the top face. To make this body in equilibrium condition, a same shear force or shear stress will be developed on the bottom face. I am applying on the top face only. I am applying the force only on the top face. To see the body in equilibrium condition, therefore automatically bottom face, the bottom face also feels the same shear stress with the same magnitude. Due to this parallel forces and are opposite in direction, the body will get a rotating motion. The body will get a rotating motion. But the equilibrium condition is, it should not rotate. Equilibrium condition is, it should not rotate. Therefore, a same magnitude in opposite direction will be created such that to arrest the rotational property of the body. Therefore, these two forces, parallel forces, are created automatically. These two parallel forces are created automatically to see that the body is in equilibrium condition. This type of creating will call as complementary shear stresses. So I have applied only on the top face, but the side face, two side faces and the bottom face, automatically the shear stress will be created. So in the problem, he is discussing if the load is applied on the top face, directly I can take it as in this side faces also the same stress. We will call it as a complementary shear stress. Whatever the stress applied on the top face will automatically seen on the same faces, opposite faces with the same magnitude, but the direction will be opposite. The direction will be in opposite, but the magnitude is same. The magnitude will be same, but in opposite direction. It will be in opposite direction. So this is nothing but a concept which is useful in the next classes. We will call it as a complementary shear stress. మనం ఇవ్వకుండానే ఇచ్చేస్తామా, ఒక్క సైడ్ మనం ఇస్తే షియర్ ఫోర్స్ ఆటోమేటిక్గా మిగతా 4 ఫేసులు, మిగతా 3 ఫేసులు క్రియేట్ చేసుకుంటుంది. కాంప్లిమెంటరీ షియర్ స్ట్రెసెస్ క్రియేట్ చేసుకుంటాయి. సో నెక్స్ట్ we need to derive a relationship between bulk modulus, shear modulus. So what is shear modulus? It is also elastic constant. It is also elastic constant with shear stress. By shear strain. shear stress by shear strain. Shear stress by shear strain. So it is also nothing but stress by strain. But we are considering shear. The shear is created in two-dimensional. The shear is created on the two-dimensional surface. The shear is created on the two-dimensional surface. So to derive this again, we are considering a square. We are considering a square, and the shear stress tau is applied on the top face. Therefore, a complementary shear stress is created on the bottom side. Due to this shear force or shear stress, the strain or the dimensions will be changed from D to D dash and from C to C dash. And the diagonal, if you see the diagonal BD, if you see the diagonal BD, its length is increasing. The diagonal length is increasing. If the CA, if you see the diagonal AC, its length is decreasing. The diagonal AC length is decreasing. Therefore, the tendency of increasing of diagonal can be written as the tendency of increasing the diagonal BD can be written as the tensile force applied along the diagonal BD, and plus the compressive force applied along the diagonal AC. Due to this compression force, this diagonal BD diagonal will be increased. It is compressing. The diagonal AC is compressing. Due to this compressing effect, the length will be increased. The diagonal BD will be increased. Therefore, here he is considering the diagonal BD. The stress in terms of stress, that is elongation in terms of stress, that is strain, is equal to the strain in diagonal BD is equal to, here the stress is shear stress applied as shear stress by Young's modulus. It is a tensile in nature. We are considering the diagonal BD, and the load is also along the BD. Therefore, it is a tensile in nature. Now, I am considering the diagonal BD only. But the load on the diagonal AC, the load is applied along the AC. Therefore, the diagonal BD will be increased. While compressing the diagonal AC. That is nothing but according to the Poisson effect. This diagonal will be increased. So it feels a tensile due to this compression effect. Therefore, I can write it as mu into tau by E, which is also a tensile in nature, because here we are considering BD, but here shear stress on this face is a negative. We will get a relation, that is mu is equal to lateral strain by longitudinal. which is a negative, but here the stress is a negative stress. Negative of negative will get a positive. Negative of negative will get a positive. Therefore, we need to add this. Both are a tendency to move the BD, its length. Therefore, I need to add this. Both are in tensile. I need to add it. We'll get a relationship between it tau by E 1 plus mu. 1 plus mu. That is the strain along the diagonal BD. Strain along the diagonal BD. Next, we need to see a graphical view. A graphical view, that is C is elongated to C dash and D is elongated to D dash. The position at now is A, C dash and D dash when the load is applied, that is shear stress is applied on the face. Therefore, what is the increment in the diagonal? What is the increment in the diagonal? BD. That is length of change in the diagonal BD is nothing but, I can write it as B D1 is the final diagonal length minus initial diagonal length, that is original diagonal length. This is final diagonal length minus initial diagonal length. That is the change of diagonal. Now I can write it as strain in the diagonal BD in terms of change of length by original length. So I can write it as change of length by original length. Therefore, change of length is nothing but final length minus initial length by original length is nothing but a strain. The final length is this and initial length of the diagonal is BD. Now draw a perpendicular. Draw this line, Amma. Draw a perpendicular from D which cuts the D dash B at E. Now take this small triangle. I need to find out the angles. Take this small triangle. I need to find out the angles in the small triangle. It is 90 degrees here given. This is 90 degrees. I need this two. I need these two angles. That is the angle at D as well as angle at D1. Angle at D and the angle at D1. Since it is a square, therefore it has a 90 degrees. If I consider this angle, therefore it has a 45 degrees at the top and a 45 degrees at the bottom. Thus 90 degrees will be equally shared. Now 90 degrees will be equally shared. Therefore 45 degrees and 45 degrees. So here we are getting 45 degrees. Here we are getting a 45 degrees. And next, here also we will get a 45 degrees. At D dash also we will get a 45 degrees. And at D also 45 degrees. So the angle at D at D1 is also a 45 degrees. Now he is writing the length in terms of D and E, that is nothing but change of length. Here the diagonal is increased by, the diagonal is increased by D1E is the change of length. So I need this length in the triangle. I need this length in the triangle. Therefore, I can write it as, so cos or sine, because both are 45 degrees, no problem. Both are 45 degrees, no problem. Therefore, I can write it as this equation, that is nothing but in terms of D1 and D, in terms of, that is nothing but hypotenuse of that triangle, hypotenuse of that triangle, hypotenuse of that triangle. This is 90 degrees. Hypotenuse of the triangle. So we are getting this side, D dash E side length in terms of hypotenuse. In terms of hypotenuse. Next, now I am considering a square, a initial square whose I am considering a initial square and I need the initial length of the diagonal BD. I need the initial length of the diagonal BD. So I can write it as AB square, that is nothing but a hypotenuse here. It is a hypotenuse. Therefore, this side plus this side. Hypotenuse is nothing but root of AB square plus AD square. Therefore, both are equal. Since it is a square, both are equal. Therefore, I can write it as AD square only. Therefore, both sides are equal. Both sides are equal. Therefore, I can write it as root 2 AD. Now, considering the above diagram and above equation, this equation amount. Therefore, I can write this upper value. I can write this upper value BD in terms of BE, in terms of BE, since both are equal. Since both are equal. Since both are equal. Very, very negligible. Therefore, I can make it as equal. Therefore, I can write it as D1 by E by BD. D1 by E, D1E, I have found it the value D1E, I have found it as D1 by root 2. Therefore, I am substituting the value. And I have found the BD value. I have found the BD value, that is root 2 into AD, root 2 into AD. Therefore, substituting it. Therefore, I am getting a relationship that is 1 by 2 DD dash by AD. DD dash by AD. So here, what is DD dash? What is DD dash? That is nothing but delta x or something else. We have derived it, shear strain phi is equal to opposite side. That is, we are taking a tan phi is equal to opposite side delta x by adjacent side of that. Therefore, I can write it as nearly equal to phi is equal to We had derived this equation in the previous classes. Shear strain is equal to opposite side. So here this is the theta. It is the theta, nothing but a shear strain. The opposite side for here is dd dash, and adjacent side for this is AD. The adjacent side of this is AD. Therefore, I can write this in terms of shear strain. I can write this in terms of shear strain. So it is also the strain in DB, diagonal. So we have two relations, both are equal. We have two relations, both are equal. That is nothing but 2 by 2, 1 by 2 shear strain. We can write as phi or theta is equal to, in the previous equation we have derived it. In the previous equation we have derived it tau by E into 1 minus mu. Tau by E into 1 minus mu, 1 plus mu. So both are equal, therefore equating these two equations, that is 1 by 2 5 must be equal to tau by E 1 plus mu. Both are same equations, that is BD strain. BD strain. BD strain only. Therefore, I need to cross multiply it. We'll get capital E is equal to 2 into tau by phi 1 plus mu. 2 into tau by phi 1 plus mu, where it is nothing but shear stress, it is nothing but shear strain. Therefore, I can write it as I can write it as 2 into G into 1 plus mu. So we can represent the shear modulus by G, by N, or by C, capital C's. All are shear modulus only. All are shear modulus only. We'll call it as shear Young's modulus. Shear modulus. So this we have three modulus: Young's modulus. Second one is the bulk modulus. Third one is the shear modulus. Three modulus. These three modulus we will call as elastic constants. Elastic constants. Elastic constants. So I need a relationship between these three. I need a relationship between these three. I need a relationship between these three without a mu. Without a mu. I need to remove the mu. I need to remove the mu, that is a Poisson ratio. And I need a relationship between these two equations. So we have derived the capital E is equal to 3k 1 minus 2 mu. That is the first equation we have derived it. That is the first equation we have derived it. And the second equation we have derived here is 2g 1 plus mu. So using these two relations, and I need to remove the mu's. I need to remove the mu's, that is, I need to remove the Poisson ratios. So I am using this first equation. I am using a relation that is moving 3k to the left hand side I am moving 3k to the left hand side. Therefore, I will get this equation. And I am moving the 1 also to the left hand side. So I will get 2 mu is equal to. So that is the first relation simplification. Now, the second relation, I am multiplying each and every term with 2g. So I am getting this relation. Now I can substitute 2 mu. I can substitute 2 mu, the value here. Now I need to multiply it. So by multiplying each term with g, so I will get this equation. Next, here 2g and again 3g again. So I need to add it. So I will get a 3g. And here e's are on both sides. Here also we have e and here also we have e. So I am making a common and moving that to the left hand side. I am making a common and moving that to the left hand side. So I will get an LCM of 3k. So 3k plus g. And I need to move this term to the right hand side. Therefore, 3k into 3g will get 9 kg. 9 kg by 3k plus g. This is the final equation between the relationships between the elastic constants. Sir, how to by heart this equation? How to by heart these 3 equations? 1, 2 and 3. So the 3 equations are begin with E only, capital E only. The 3 equations are begin by capital E only. Next, the first equation have a bulk modulus. The first equation have the bulk modulus. So we have 3, that is 3-dimensional. It is a 3-dimensional. It is a 3-dimensional. It is a 3-dimensional. And a second equation, if you see the second equation, it is, if you see the second equation, it is a shear modulus equation. Shear modulus equation. Therefore, it is a 2-dimensional. It is a 2-dimensional. 2 need to be here. 2 need to be here. 2 need to be here. So it begins with 2. It begins with 2. Therefore, 2 and 1 only will be having in the equation 2. It begins with 3. It is a 3-dimensional. Therefore, 3, 2 and 1 are present in my equations. Next, third equation. How to remember this? How to by heart it? How to by heart it? So you can use or remember kg, both having the kg, both having the kg, both having the kg. In the denominator, we have k plus g. In the numerator, we have only kg, and 3 as well as 9. So we need to by heart 9 kg by 3 k plus g. It is equal to E. So with this, a relationship between the elastic constants are completed. Therefore, the second chapter of this unit is closed. The second chapter of this unit is closed. So here in the second chapter, main important is 3 derivations. First derivation is volumetric strain. Second derivation is a relationship between E and bulk modulus. Third derivation is a relationship between E and shear modulus, where E is Young's modulus and G is nothing but shear modulus. So with this, the second chapter is closed. Any difficulty in understanding, please contact me. So with this, I am closing this section.